Good morning. My name is Balakrishnan Raman, and let's do an overview of AMD Pensando's high availability implementation. Sanjay, can you move on to the next slide? Yeah. So our design goals that we had are so all connections set up before switchover should work reliably after planned and unplanned switchovers. This means there should not be any connection missing after switchover, because if there are any connection missing, then that will result in connection failure. Zero downtime planned switchover, less than 2-second downtime unplanned switchover. So this also kind of requires no missing connection after switchover, as all connections need to resume after switchover. Data packets should not be dropped due to flow replication delays. Sync connection setup and tear down at a data path rate to support a high CPS. So basically, we support a very high CPS in the sense connections per second in the standalone mode, and we wanted to retain the same with a high availability as well. So we wanted to basically with a sorry, I'm hearing okay. So with the high connections per second, obviously we have to do the setup and tear down has to happen at the high connections per second rate. So we also wanted to do the sync of connection setup and tear down also at the data path rate, so that we can support that high CPS rate. And if you are trying to sync with the data packets, so wanted to sync only the required packets, so that not sync all the packets with the secondary, because we wanted to conserve the packets per second for the data traffic. So these are the design goals with which we started to design and implement our high availability feature. Okay, Sanjay, you can go on to the next slide. Okay, so with that we started exploring a few flow replication options. So the three options that we started exploring were one is the asynchronous flow replication. Then the other one is that inline flow replication with the secondary forwarding. And then the other one is inline flow replication with primary forwarding. So the first option, asynchronous flow replication. So basically, flows are established between endpoints even before they are synced to the secondary. What that means is basically syncing happens offline after flows are set up in the primary, and basically primary sets up the flow, and also it forwards the packet to the endpoint even before it syncs it to the secondary. So secondary doesn't have the state yet. And then offline, the primary goes and syncs the state with the secondary. So what this means is there is a possibility where connections could be missing on any unplanned switchover. In other words, that is something we term here as that it's not reliably synced. And so those missing connections will not be able to resume after switchover because there is no connection. So without the connection, then all the packets that come to this new node after switchover, they will get dropped, so they cannot resume. So that's the asynchronous flow replication, where the synchronous is happening offline. So then we looked into the next option, where say we do inline flow replication. What that means is basically flows are synced inline. So when we receive a data packet to set up the connection in the primary, we set up the connection in the primary, and we use that we redirect that data packet to the secondary, so that with some metadata, so that the secondary can also set up the connection. Thereby, the state is basically replicated to the secondary. And then in this particular option, the secondary itself will forward that, because the sync happened with the actual data packet itself. The secondary will forward the data packet towards the to the endpoint. So there is no acknowledgement that comes from the secondary in this case to say that yes, the state has been replicated. So second, because as soon as the first packet that sets up the connection in the primary, it is redirected to the secondary, and the secondary sets up the connection, and then it forwards to the endpoint. So the advantages here are obviously the packets are not let go to the endpoint. It is first replicated in the secondary. So basically the connections, the states are replicated. They are there in both primary and secondary. So the sync is kind of reliable. So no connection is missed in the secondary, as flows are first synced before sending packets to the endpoint. Also, we use the data packets, and the data packets are redirected at the data path rate. So it happens at the data path rate, and we can sustain the high CPS that we support in our data path. And also, we don't do any buffering. So there is no, no drops due to any sync delays or anything like that, as we redirect the actual data packet itself to the secondary for syncing the state. So the disadvantage with this approach is one where the secondary is forwarding the packet and it's not sending an acknowledgement back. So what that can cause is that, let's say there is a connection. Let's take an example of a TCP connection. Let's say the connection is in the process of getting terminated. So that means it's basically sending a last tag or reset packet. And the control packets of TCP is what we try to redirect to the secondary to sync the state. So the last tag reset will be redirected to secondary to basically sync the state of terminating the connection. So if this last tag or reset, it gets dropped before going to the secondary, then what would happen is basically primary has seen the last tag reset, so it will clean up the connection. Whereas the last tag reset redirected to secondary didn't reach the secondary, and so secondary will still maintain the connection. So kind of the connection is now out of sync between the primary and secondary. So if it's last tag, obviously the endpoint will retransmit the FINAC and last tag, and it will again end up in the primary, but primary doesn't have any state for it to either forward the traffic or redirect it to the secondary. So that's a disadvantage by not having the acknowledgement coming back from the secondary to know whether the connection has been really synced or not. So then we went and explored the other option where we do inline flow replication. But what about getting the packet back from the secondary and let the primary do the forwarding finally and not the secondary? This way, it will serve as an acknowledgement of the replication, state replication, and the primary also will do the, will receive the inbound packet as well as it will forward the outbound packet, kind of consistent there. So this option is same as the above option with respect to inline forwarding with an additional acknowledgement. So where the secondary, after setting up the flow, will redirect whatever data packet that was sent from the primary to secondary. And so this lets the primary know that the state has been synced. And then it will forward the packet to the endpoint, knowing that the connection has been replicated with the secondary. So it has the same advantage of inline forwarding, whatever that we discussed in the previous option. And in addition, the issue with respect to the last tag reset getting dropped. So even though, let's say it gets dropped, because if it gets dropped, the acknowledgement won't reach the primary. As a result, the primary won't clean up the state. It will still maintain the state, and retransmission has to happen from the endpoint, at which and the primary still maintains the state in this particular case. So it will still try to send the redirect to sync the state with the secondary, and thereby it will converge. So that way, the acknowledgement allows us to keep the connections in sync. So
do you expect that? Can I ask a quick question? Do you expect the acknowledgement before sending the packet to the end host, or?
Yeah, so that's why I mentioned there that the acknowledgement comes and which is the actual data packet, and that is the data packet which we forward to the endpoint. Yes, we expect the acknowledgement to come, and that is the acknowledgement which has the data packet which is actually forwarded to the endpoint.
Is it possible, just a thought that if we can forward the packet and send it to the secondary and the act can happen sort of offline, not inline?
But again, you have the same issue, right? Where you forwarded the packet, so the endpoint is going to move forward, and then it is going to send subsequent packets, or it's going to basically terminate the connection. But we the act might not come because there can be drops. So
But
inline.
the problem is this is doubling the bandwidth.
Sorry, Gerald, I couldn't hear you.
So the problem with this last proposal is you're doubling the bandwidth that you're using, that you're doubling the PPS you're using, you're doubling the bandwidth you're using to do this. And it's super costly.
Is this being done for packets when you're in the established state, or only when there are state changes?
So only when there are state changes. So basically only the control packets, and even for the control packets, yeah, we are trying to do some optimization to basically sync only the required ones.
So doesn't that lead to like another situation where like when you're in the established state, the primary like doesn't time out because it's it's not idle, the flow keeps moving, but the secondary could time out the connection because it's not seeing any of the packets while you're in the established state? Isn't there like don't you have to like periodically keep the secondary alive?
Yeah, so basically we have a coordinated aging between the primary and the secondary. So okay. Yeah, so like you said, yeah, that in the secondary, I mean, the aging process basically happens in the primary. In the secondary, there is a kind of aging process, but that timeout is quite large. So basically, as you said, there is a coordinated exchange between the primary and secondary to keep the connection alive if data is getting forwarded in the primary.
Okay. Okay. Thanks.
So the inline. So yeah, so Gerald, to your question, yes, it's kind of a trade-off. Like, I mean, to make the replication reliable, yeah, there are some extra exchanges that we had to do with between the primary and the secondary, and also, yeah, so we are trying to also at the same time trying to optimize to see what is the required, state-changing packets that we can sync between the primary and the secondary.
And I think if you may or may not have been here, but I think Excite did do some interesting measurements on what happens, at least in Azure today. And it's when, there's some shorter timeouts of aging. So like, for example, if you receive a fin and you don't receive the fin ACK within 5 seconds, I think they tear it down. Or if you receive a fin ACK and you don't receive the ACK within 5 seconds, they tear it down. So there's short timers used along with the aging timers that you may be able to take advantage of, just knowing that if you receive the fin, that the other side will tear it down regardless of receiving the final fin ACK. So there might be some games you can play there, and it's really a matter of which timers we define, right? Timers for the control packets and timers for the aging. They can be separate. So we shouldn't talk about it today because it's like this long conversation, but I think there's optimizations we can look for to reduce the number of packets required.
Right. So if we suppose, for example, if we get an ACK for for a state that is in the teardown sort of bucket, right? And we don't have that flow anymore because we have sent it to the endpoint and we have already received and we have already deleted that flow. We can always ignore that, right?
Yeah.
So on and so forth.
Yeah, we can ignore that. I mean, see here. I mean, the particular case that we were talking about was The one where, yeah, so we tried to send the last tag to the secondary and it got dropped, and but let's say the primary kind of cleaned the connection, right, with the second option particularly. So the endpoint wouldn't have received the packet, so it will keep retransmitting. And in that particular case, I mean, the case what I was talking about was with respect to second option was that we don't have state, but the endpoint is retransmitting.
Yes. So I get the
that,
advantages of this one. It's just like super heavy on bandwidth and PPS, which when you add it up is tremendous. So it's 6 packets here that we're talking about, and they're going, 6 packets into one DPU, out that DPU to the mate DPU, back from the mate DPU into the DPU again, and then out again. So it's like going through too many times. Like if you count it all up, it's like 6 control packets which are coming in and out twice. And at 3 million times 6 is 18 million, and then you double that, now you're up to 36 million packets per second just in syncs. And that seems, well, it's not, doesn't seem excessive, it is excessive, because you're not going to have much left over for user traffic. So that's why I think we need to, I get the benefits for sure, but we need to optimize it because it's just too much messaging, and quite frankly, it's sending whole packets. In fact, when the other side, all it needed was to update its state, not to receive whole packets. But we'll talk about that later too. But anyways, we get these 3. That's good. We should go on with your presentation so we can absorb, everything you have to say.
Okay. So the third option is what we have implemented. So yeah, so let's, Sanjay, can you go on to the
just
next
a
slide?
quick question, Balki. You talked about that, of course, only the control packets are synced. So how about, besides the connections, do we not want to synchronize any statistics or telemetry data between primary and secondary?
So statistics wise, see, packets transmitted and received, I mean, there are control packets that we receive in the standby, but all the other data packets, they go only in the primary. So so basically we maintain stats in both the primary and the secondary, and we present that to the controller. So basically, the controller can present that as the stats coming from the primary and the secondary. Like for instance, one case that I can, one example that I can give you is like before switchover, you will see the packet the packets and bytes transmitted and received that will be incremented in the primary, but not in the secondary. And then after switchover, it will, for the same connection, it will be updated in the secondary, or rather the secondary becomes a standalone at that point. So basically, controller will kind of aggregate that stats and then present it as the number of packets transmitted and received on that connection.
So there are separate control packets that essentially synchronize all these statistics between primary and secondary, besides the data package.
No, we don't do that.
Yeah.
This isn't even a goal for this. The SDN control plane gathers up the information, aggregates as needed. In a controlled failover, that's not even a problem. It's just aggregated. And in a total failure, quite frankly, we don't know what's going to be where. But the control plane will gather that, or it will be pushed to the control plane, one or the other, probably pushed from periodically. But with this HA program doesn't have a goal of maintaining all the stats. That's would be excessive. Like we would have no bandwidth for anything at that point. It's not really something that's doable.
Okay.
But we do have the notion of even in Sonic, you can have a pub sub interface and you can push statistics periodically up to the different databases, etc. And that's what we plan to do. And then aggregate. SDN control plane will aggregate.
Thanks.
Okay.
Hey, one Hi, Balki. Yeah, so I have a basic fundamental question. Like, so when we replicate this state right to the peer, like, do we uh, just wanted to confirm, like, when the first packet goes on the other side, it carries the, like, for example, if it is a VXLAN encapsulated, the policy said encap it with VXLAN and ACL said allow. So I think like we will be carrying this derived data, and the other side will just cache it, right? It is not going to do the CPS processing again. Is that right?
So yeah, so the policy evaluation and so yeah, we do carry metadata when we redirect the packet to the secondary, and that metadata yeah has some of these information like the policy evaluation result, whatever that happened in the primary is carried to the secondary, and some rewrites. Yes.
Okay, so like some of them may need to get fixed. Like if they share the same WIP, like source IP, right, in the encap header, probably that doesn't need to get fixed up. But if they are different, then this doesn't match, right? Like,
So with respect to the virtual IP, yeah, we use the virtual IP. I will come to those details in the subsequent slides. There is a common virtual IP that is shared across these HA pairs, and
okay,
we use yeah. I'll come to
okay,
those slides, Suresh. Yeah.
sure, yeah, thanks.
So with respect to the deployment topology, so one topology I have showed here where so we have this dash appliance where there are one or more, I mean, DSEs. I mean, DSEs is the AMD Pensando terminology. You can, yeah, it's equivalent to the DPU. So one or more DSEs, and each DSE in the appliance is paired with another DSE in the other appliance. And these DSEs are dually connected to both the TARs, and in turn TARs are connected to the spines in the class network. So with our implementation, so we have multiple, sync channels between these DSEs. So we have so as you know, we have a P4 data path, and we also have a software data path. So there is a P4 data path channel, which is the one that does the inline flow replication. Basically, as and when the packets come, the redirecting the packet with metadata, all that is taken care in the data path inline. And that is the channel that is used to do that. And then there is another channel, which is the software data path channel, and that is used for sync like bulk sync. Bulk sync happens when one DSE that is already existing with state and a new DSE comes up and it pairs up with the existing DSE. So all the existing connection state has to be synced as a bulk sync. So the software data path channel is used for bulk sync, and also like we talked before, coordinating the aging between the DSEs. So this deployment, whatever I have shown, is an appliance with multiple DSEs. So we can also have other. You can also think other topologies, like you can have just two DSEs which are doing the HA pairing connected to the TARs, or you can also think about DSEs within the smart switch doing the HA between them. Okay. Yeah. So the option that we implemented is the inline flow replication with the primary forwarding. So I will go into a little bit of details here. So basically, so as you see in the picture there, so we have the primary DSE and secondary DSE. So basically the idea is we present this primary DSE and secondary DSE as a single logical DSE. So what that means is whenever there is, whenever you have packet, I mean connection setup between VMA and VMB. Let's say you have only a standalone DSE or one DSE. You basically set up the connection in that DSE, and then you forward the traffic to the VMB. So that is what we are trying to do here. So what we are trying to do here is we are trying to set up the connection in the logical DSE. That means it's reliably synced on both the primary DSC as well as secondary DSC before we forward it to the VMB. So flow is basically set up and cleaned in the logical DSC before we forward the packets to the endpoint. So how we set up in the secondary DSC is by redirecting the data packet. I mean, data packet in the sense it will be the control packets in case of TCP, like the SYN fin reset, and for basically for UDP it's the data UDP packets. And the packets that are redirected will also have additional metadata. And these are all taken care in our P4 data path between the primary DSC and the secondary DSC. So the metadata carries policy evaluation and the rewrites from the primary DSC to the secondary DSC, and secondary DSC uses that. We will come to the config, config related, things in the subsequent slides. So the coordinated.
I don't understand something. You're saying SYN, fin, and reset. Well, if you do a switch over and you have FIN-ACK and ACK, right? And how does the state machine know where it is if you're only sending a fin? Like, what if it sent the FIN-ACK and then it's only missing the ACK? How would the secondary even know that?
No, Gerald, what I meant by fin is all the FIN-ACK ACKs. So.
Oh, okay. Well, that's important because that triples the amount of data being sent. So this kind of indicates that you're sending us, at the beginning and at the end. And of course, you can't close at the fin for sure, because then you would never see the FIN-ACK at the end point. So we should at least write in what we're really doing, because it's not. You could say SYN sequence, fin sequence, maybe.
Yeah. So Gerald, as you know, so we our base implementation was all 6 packets: SYN, SYN-ACK, ACK, fin, FIN-ACK, ACK. All of them are synced, and we are also looking into the optimization of reducing the number of those 6 packets to few packets to get the same effect. Yeah.
Okay.
All right. I have a question. That's Chris. You've been describing the synchronization mechanisms mostly, but what I haven't heard really is just a discussion of what happens when a failure occurs. How does the traffic switch from the primary to the secondary, et cetera, practically?
Because that's a different, I think you'll get that. That's a different mechanism.
Yeah.
Okay.
So we will.
It's there in.
You will cover that.
You have to wait for that. I think he'll cover that. There's a couple mechanisms they can use for that.
Okay.
Yes, Chris. We will discuss unplanned switchover, planned switchover in the subsequent slides. Yeah.
Thanks.
Sure. So so coordinated idle aging is taken care by the software data path between the primary and the secondary DSCs, and also bulk sync, which happens when a new DSC pairs up with an existing DSC. So these packets that are redirected for syncing the state, they can get dropped. So when they get dropped, this will those drops will be perceived by the endpoint as network drops, and it will basically trigger retransmissions. At which point, again the sync, the redirecting the packet and sync will take place, and it will the sync. The replication will converge, and the packet will go to VMB. We also have periodic heartbeat exchanges between these primary and the secondary DSCs. So these exchanges are to detect the peer reachability. In any case, let's say the primary DSC or the secondary DSC goes down, these heartbeat exchanges will fail. As soon as they fail, the DSC takes over, transitions to a standalone role. When it transitions to standalone role, it doesn't sync, it doesn't redirect any packets to replicate the state, because there is no peer at that point of time when it is in standalone state, and thereby we won't be keep dropping the packets as soon as we know that the peer is down.
I think that leads to split brain, but I have another question before we get to that. Is you can sync to the secondary, and you can send the, like a SYN packet, for example, to the secondary, and then it sends it back to you, and then you forward it on. And so now you're both synced, but then it gets lost between the primary and the endpoint. And so it has to resend, but now that it's resending where both devices believe that they have a connection already.
Right.
What happens? So
but
at least we don't.
Gerald, that could happen. That could happen anyway, right? I mean, that's just like the network could drop a packet anywhere, right?
No, but then I wouldn't have a. If I have a single device and I receive a SYN, it gets dropped, and then I receive another SYN.
Right.
My point is, you just need to take care of the case.
Yeah.
What happens? Because it looks like a SYN attack at that point, but it's not.
Yeah, it's like, yeah, we do handle the retransmission SYN, Gerald. Yes, that SYN will be retransmitted by the primary DSC.
The second one that comes,
Yes,
that's
yes.
the same as the first.
Yeah, I mean, it's not exactly same as first. I mean, with respect to our implementation, yes, there is a difference because we keep track of the state in the primary, right? Because there is some change in the state, so we know that it's a retransmitted SYN. But yeah, it is handled. We don't drop the retransmission.
Now,
even though, yeah.
Okay, so if you on that note, are you requesting the secondary do anything but copy the state into its, like once it opens the connection, is it just copying the state in, because it doesn't really need to do any calculations, the primary's already done it. So are you suggesting that the metadata would just say, hey, just go update this connection with the state and forget about any calculations you're trying to do? Or are you actually asking it to do the same thing the primary already did?
No, so with respect to, I mean, yeah, this gets into our implementation. So some of the things we need to do, see, we have to tie it to some of the resources that have been allocated in the secondary, right? The connection has to be tied to that. So for that, you need to do the corresponding local lookup. But mainly where the copy happens is the policy evaluation result, right? We need to use whatever that the primary has sent, because the config that is getting pushed to primary and secondary, they are not in sync at any instant. They are eventually becoming consistent because the controller is kind of pushing the configuration to each and every DSC one after the other, right? So that's why the policy evaluation result, we send it between the primary and the DSC, and the secondary DSC basically takes that and it uses that for setting up the connection. Likewise, the rewrites, it does. But in addition to that, with respect to our implementation, there are some things which there are some resources to which we have to tie up the connection. Those resources are what we are doing, like, I mean, some ENA related resource and things like that.
Okay, but you don't have to rerun the policy on the SYN on the secondary. You just assume the policy passed because the primary said so, and then you just create the connection, right?
Right.
Okay.
Yeah.
That's
the decision on the primary, whatever is the decision on the primary holds on the secondary too.
Yeah.
So I think there was another question in terms of we may need to fix up some things, etc. I think those fix up is what Balki is referring to. There are some pieces where we have to tie it to the hardware resources, for example, the next stops that we use and things like that. Those things happen on the secondary, but the policy itself, whatever is the primary's decision, is carried.
Okay.
Hey, Balki, one question about the bulk sync. So this is the case where the secondary DSC is newly coming up, and I'm assuming you're synchronizing, a whole bunch of flows from primary to secondary, right? How does it, ensure the state that properly maintained in secondary DSC, right? And if this actually works, why wouldn't you use the same approach for even the inline instead of sending the packet? Why wouldn't you send the states?
No, the bulks. So the bulk sync is happening kind of offline, right? So obviously there will be we cannot keep up with the state. So yeah, I will come to the bulk sync part where we will kind of catch up to the state. Like, I mean, I'll tell you what we do there.
Yeah.
Okay.
I think we also described that as
If I'm-
perfect sync, and perfect sync doesn't happen you know, in real time. It is a background task, and when it's done, because you're also doing the synchronization you're talking about here, then you're done. You do one perfect sync. When you get to the top of the table, you're done. So I think we described that already, but I'm sure that we can also, because this meeting's only an hour, we're not gonna, but we can discuss that. Definitely, there's techniques, but it is asynchronous. It's not something that needs to, it actually occurs while doing real-time sync, and that's why it works. And it's described in the perfect sync in the HA document that we published.
Okay.
Do you want me to move ahead, Palki?
Yeah, move ahead. Yeah. Yeah. The next slide. Yeah. Yeah. So so the HA, so the primary, secondary HA. So basically, it's basically the active and the standby sync that we do. Wherein the standby, the secondary is like acting like the standby, wherein it doesn't forward any traffic. The active is the one that is forwarding the traffic. But at the same time, it's not like the hardware is acting like a active standby. What I mean by that is, it's not like DAC1 is completely forwarding the traffic and DAC2 is not forwarding traffic at all. The hardware is still active, and how you do active, it's the ENI based active. What that means is basically, so we have the virtual IP or the PA IPs. We give the virtual IP that is shared across these DACs. So both share the same IP, and we have two virtual IPs. So the way these virtual IPs are configured in these DACs are as shown in the picture, wherein let's say we have VIP1 and VIP2. In DAC1, VIP1 is primary and VIP2 is secondary. And in the other DAC, it's the other way, wherein VIP1 becomes secondary and VIP2 becomes primary. So basically, DAC1 will be getting traffic for VIP1, which is primary, and it will do the forwarding for that. And whereas the DAC2 will do the forwarding for VIP2. And basically, how you attract traffic for the corresponding virtual IP in DAC1 and DAC2, it's all based on BGP configuration. Wherein VIP1 becomes DAC1 becomes the favorable node for virtual IP1 to forward the traffic, and likewise virtual IP2 becomes the favorable node for forwarding the traffic in DAC2. And then what the controller does is, so we have a bunch of ENIs that are being serviced by these DACs. So out of these DNAs, some DNAs will be, the controller will associate some of the ENIs to virtual IP1 and some other set of ENIs to the virtual IP2. So that's a way. So some ENI will be made active in the DAC1 and some ENIs will be made active in DAC2, and the DAC does the forwarding for those respective ENIs. In case of any failure, let's say one DAC fails, let's say DAC1 fails and DAC2 is the only one that is surviving, then it basically at that point, it owns both the virtual IPs, and it basically attracts and forwards traffic for both the virtual IPs. So all the ENIs will be kind of active at that point in that surviving DAC.
Malky, how does in the third mode or third option you described, where the primary does the forwarding after synchronizing with the secondary, let's say one of those devices fails, how does the surviving one know not to rely on the other device at that point and just forward by itself?
Right. So there is a heartbeat that is being periodically exchanged between the DACs. So at any point when one of the DACs go down, there is a disruption in the heartbeat exchange, and we have a configurable, heartbeat interval and count. After that heartbeat count multiplied by the interval timeout period, it basically the DAC declares that the peer DAC has gone down, and so the virtual IP, whatever that is configured in that DAC, they all transition to a standalone role. So both whips, like for instance, DAC1 goes down, DAC2 will not get any heartbeat responses from DAC1. So DAC2 will basically move the both the virtual IP 1 and 2 to standalone role. At that anytime the data path sees that the virtual IPs are in standalone role, it doesn't do any packet redirection. There is no state synchronization at that point because it's a standalone. So it continues to forward directly without sending it to the other DAC.
Yeah, it makes sense. It'd probably be nice to have some kind of a state diagram that shows the states these point to at some point.
Yeah. This is a dangerous state, by the way. There's lots of bad things that can happen in split ring, but let's move on because there's only a limited time left.
Okay. Yeah. So the node pairing process. So basically, yeah, I'll go over what happens in our DACs when the pair up happens, right? So basically, let's say DAC1, DAC2, and DAC1 is the one that comes up first. Let's say it boots up. As soon as it boots up, the controller configures and it kickstarts the finite state machine, HA, the high availability FSM, we call it, the finite state machine. So there is a API from the controller to start the FSM. So basically, the controller needs to configure, and we provide a control. So there is a control, basically a gate for the controller to when to start the kickstart the FSM. Basically, it can, even though it, let's say it configures just the HA the high availability parameters, but it doesn't configure any other thing. It doesn't mean that we will immediately start the high availability, pairing process. So there is a control for the controller where it even after all the configuration, it will come and issue this HA start. At which point the FSM gets kickstarted. It binds the, so there is a, in terms of configuration, there is this inter DAC IP addresses. That is the one that is used to communicate between the DAC1 and DAC2. For the those are the IP, endpoint addresses for the inter DAC channel. So we bind to that, and then the virtual IPs will go to dormant standalone roles. The dormant means basically I mean, it is kind of, I mean, in this case, okay, before explaining dormant, so it goes to standalone. The reason being that there is no peer at that point, right? Because DAC2 has not come up yet, so it goes to standalone. In addition, we have another control. So it first goes to a dormant state. The dormant state is where we have not advertised the virtual IP, so we are not attracting any traffic. We are in a role, in a dormant role. Only when the controller comes and it issues take over the admin roles, that's when we take over the roles. So I'll explain why we have the dormant role a little later. So we take over the roles. So at this point, as you see in the picture, so just so as you see in the picture, so both the virtual IPs they go to standalone and standalone. The reason being that when the FSM started, it has already started the heartbeat exchanges. But given that there is no peer, there is no response, so it goes directly to standalone, saying that there is no peer for me to do any state synchronization, so it goes to standalone. And now any data path traffic, we set up the connections and we start switching the traffic. And a little later, let's say, so all the states are being set up at this point. Little later, let's say boot up happens, and the same thing happens in the DAC2 where it goes through HA start, at which point it will start exchanging the heartbeat, bind the DHCP IPs, and then start exchanging the heartbeat, and then they see that there is a peer. As soon as they see that there is a peer, the DAC1 will kind of go immediately active for both of them. Basically, the point being here is that this is the DAC which is still will be receiving the traffic for both the virtual IPs. There is no, this DAC has not advertised the virtual IP yet, because in dormant state, we don't advertise the virtual IP yet. We don't give the control yet. So it becomes active, and then it starts all the sync. Basically, There will be existing connection for which we do the bulk sync. There will be real-time new connections that are being set up, and then connections that are being toned down, which will be inline synced through the P4 sync. So all those sync that will happen. And at the end of the bulk sync, the P4 sync is kind of ongoing, though the picture doesn't show it. It's kind of keep going as and when there is a state change. So the DAC2 becomes a dormant, and then the controller, as I said, has this control to come and say activate the admin role. So it activates the role, and that is when the virtual IP takes the role. So in this case, what would happen is virtual IP1 becomes standby. So virtual IP1 in the DAC1 continues to be active, and virtual IP2 becomes active. Basically, its admin role is active. So this is kind of a preemption here, where even though VIP2 is active in DAC1, the role is preempted by DAC2 and it becomes active. So the dormant basically is a control given to controller where we don't want to preempt and DAC2 directly take over and start switching the traffic. Microsoft wanted not to have that kind of behavior. So we wanted to have a control there. So that's why it first goes into a dormant where even though it is prepared to be ready with all the state, it still doesn't take over completely all the traffic by doing preemption. So and then once the control comes, then it will go and do the preemption.
Yeah.
Okay. Yeah, so with respect to sync.
Back here, one question. So in the previous case, when DAC1 and DAC2 both are independently in dormant state initially, right? And only when the active is triggered, they would start the heartbeat. So is there a race condition where both of them could be, forwarding traffic or advertising for VIP for a period, small period, or is it really controlled and well connected node 2?
No. So the heartbeat exchange happens using the inter DAC channel IP address. That is not using the virtual IP address. So the virtual IP address are not so for instance, when the DAC2 comes up here, right? Until this point, the activate HA admin role, the virtual IP is not advertised from DAC2 at all. So DAC2 doesn't get any traffic until this point.
Yeah, but you really want to make sure that the heartbeat is established between these two, so you would know their role before you started that advertising for the VIP, right?
Yes. Heartbeat will go through because that is not using the virtual IP address. That is using a different IP address, which is the inter DAC channel IP addresses.
Okay. I think we understand. Thanks.
Okay. So just to touch upon this, the sync mechanism that is happening during the para process, right? So yeah, this is kind of a involved one. This is always a challenge because you have basically during the para process there is an existing connection that needs to be bulk synced to the peer, and at the same time. So these are all the things that are happening during the already set up connections. There are teardown that are happening for the existing connections, which are aging and endpoint termination of TCP connections. And then new connections that are getting set up during the para. And there is also, so this is a, something that I wanted to bring it up here. So there is also,
yeah, I think we'll go over not everybody in this audience will know what resimulation is.
Okay.
We are introducing it, and I've sent some documents to some of them, but yeah, we can talk about the resimulation at a different time. But definitely you've got it down. Yes, it's new connections, teardowns, flow resimulation, and already set up. There's definitely all this is true, and then we'll send out documents on resimulation.
Okay.
To everybody so that they understand. Yeah.
Okay, sure. So we have the bulk sync. So basically, yeah. So in our implementation, so we do track this existing connections with the connections that are newly getting set up. And so as I mentioned earlier, our software data path takes care of doing the bulk sync of the existing connection. And P4 data path, it's doing the inline sync of the connection setup and the termination. So like you said, while we are doing the bulk sync, there are possibilities where there can be change in state happening to those existing connections. So we are basically doing a combination of both, bulk sync at the software data path as well as the inline sync from the P4 data path to keep up with it. Okay. So, so Chris, so you asked about that heartbeat exchange. So just wanted to capture on that. So the unplanned switchover is basically is through. I mean, we detect that through the heartbeat. So basically, in the stable state, the heartbeat messages are exchanged between the DSCs. Periodically, they are exchanged. So we have something configurable heartbeat timeout and counts. Which are configurable, both are configurable. And let's say if DSC1 goes down, the DSC2 keeps sending heartbeats, and obviously it's not going to get any response. So after a count of consecutive heartbeat misses, then it will basically transitions the role to standalone. At which point any received data packet is not redirected to the peer. It will directly get forwarded. So you won't see any more drops of those packets that are going between DSC1 and DSC2 and getting dropped because DSC1 is not there.
Yeah, thanks. That makes sense. Would this timeout typically be a lot shorter than, let's say, LFD timeout or any kind of SDN control timeout? This should be like the fastest behavior.
Right.
Like tens of milliseconds, or what do you have in mind?
Correct. It should be in millisecond range.
Okay, thank you.
Is there any
so I want to go
QoS?
back. Okay, go ahead.
Is there any QoS requirements for the heartbeats? Do you mark the DSCP all across the network or something?
Yes, we have a DSCP for these heartbeat messages. Yes.
We happen to use 6 different priorities in our network, but different
Okay.
clouds will use different clouds will do that differently. I do want to go back over like a couple slides before that where you said that the bulk transfer. If you update anything that's in the the perfect sync table, in other words, the connections that were already established, not the new ones that are dynamically being established. If you update for any reason one of the connections in the ones that were already established, it moves automatically to the dynamic sync. So you don't retransmit state from an old connection after you've updated it dynamically. So it would no longer exist in. We describe that in perfect sync as colors. You move to the next color and you send all the old color across the bulk. But if you update anything in the old, then it just basically becomes a new color, or in case of Pensando, I think they use timers. But that is a subtlety in that anything in the perfect sync that gets dynamically updated itself moves it into the dynamic range and no longer in the perfect sync state. Do you know what I mean? There's 2 things happening. There's the asynchronous thing happening, which is the bulk sync, and there's a dynamic thing of new connections. Anything that happens in the bulk sync dynamically moves that connection over into the dynamic state automatically. You don't have to resend that in the bulk anymore.
Right. So that's what. So we have the software data path doing that asynchronous sync, which is the bulk sync, and the inline sync from in the P4 data path is the in our terms it's the dynamic sync. Yeah, there is some kind of coordination between these two things.
Yeah.
Mechanisms.
Otherwise, you'd be doing it dynamically and then sending it in bulk, and that would screw everything up. But just a little subtlety there.
Yeah.
Hey, Gerald, just to make sure I understand what you said. So the states that are synced in the bulk sync, once that is established, that basically any change in that will become now dynamic sync.
Yeah. Once you, it's dynamic now because you just update it. You don't want to resend an old state.
Right.
Yeah. And you can do that. I in perfect sync described it by colors, like you move towards incremental colors, and whatever is behind you is a different color. But you can do it with timestamps as well. But once you update anything dynamically in that asynchronous table, which is the the bulk sync thing, you have to move that. You no longer will retransmit that in the bulk sync. You'll just move it to the dynamic sync, and now everything will be fine.
Is this how you basically say like what the event coalescing or state coalescing happens?
Pardon?
So I'm trying to understand, Gerald, that if there is some sort of a race condition can happen, right?
There's no race condition here, actually. It's like you're either in bulk sync or you're not. And if you're not, then you're doing dynamic sync. And so now if anything is in the bulk sync table, which is like a previous color or previous time, and you update that because a new packet comes in, you're going to shut down that connection or whatever, you're going to do that connection. You're just going to do the normal synchronization, and that connection no longer be in the bulk state, because now you've updated either its timestamp beyond the bulk sync or a color, like I suggested. You moved its color to the current color. So there's no race condition there. It's like if anything happens in the bulk state, that forces it to being dynamic now, because you're going to update the state to the other side. It just becomes dynamic and automatically. So there isn't a race condition.
So no, I understand what you're saying. So we are trying to avoid, getting out of sync by this color or timestamp. So probably the way I'm understanding this thing is that the bulk sync starts by taking a snapshot of current state, and anything after that is all.
Whatever color it was, anything new will be a new color.
Right.
So that means anything old would be blue and anything new would be red, like say, for example, or a timestamp, or you can say anything before this time, because everything is timestamp. Either way, it doesn't matter. You do take a snapshot. When you do the bulk sync, you're just going through a table bottom to top or top to the bottom. It doesn't really matter. And if it's the old color, that's part of the bulk sync, and you send it across. Or if it's before a certain time period, you send it across. So it is like a snapshot, because you either move you memorize the time you did that, or you memorize the color. It's not your current color or whatever, but yeah, so it's like a snapshot.
Got it. Thanks. Thank you.
And it can be done now asynchronously. Now it doesn't need to be done in real time. It needs to be done fast, but it doesn't need to be done as fast as a dynamic sync. You just go from the bottom of the table to the top of the table, moving everything across. That's either before a time frame or before a color that you're on.
Sure. Thanks.
Hey, Gerald, one clarification. So the bulk sync of, say, the previous color, all that data, is that sent multiple times? How do we, or is that only once?
Usually only you need to send it once. You go from the bottom of the table and you just analyze every connection and say, was this before this time or before this color or whatever? And if it is, you send that across. You go to the next one, the next one, the next one until you're finished. Now you can send, we can argue whether you should send multiple, messages across in one message or not, but essentially that's what you're doing. And you're skipping over anything that's dynamic. If it's in a dynamic state, like it's after that time period epoch, or it's in the new color epoch, you don't need to send that across. You don't need to send things that were before. So you need to transfer the table only once, and you only transfer the things either before the time frame or before the color change, and that's it. And you do it once. And by the time you get to the top, you're sure that it's in perfect sync, because while you were doing that, you were sending all the dynamic updates. So therefore, as long as they keep up with the dynamic connection updates, and now you traverse the table once, you are in perfect sync at that point.
Okay. And is there an acknowledgement from the peer to confirm it's got synced?
That's implementation specific here. We can talk about that people will argue that. But the general principle is the perfect sync is go through the table once and only once, and then because you're already doing the dynamic updates in parallel, like you would normally do. That's the idea of it.
Yeah, there may be something, where there are interleaving updates for the same connection reaching to the secondary. And in that case, you are going to ignore the older one, right? And then at that
Yeah.
time, that might happen.
Yeah, I would think that would be true. That's a very, very small window, but yeah, I think that would be true. The right thing to do. Okay, let's go.
Okay.
I'm assuming this is going to be a pull request somewhere so that people can like really go through this in detail. Is that the intent here?
Yeah, we can. Code bug.
I heard we can, I think, but I don't know who said it. I don't know if that was AMD or somebody else.
That was me, Sanjay. Yeah, I think we can. The presentation itself, we can share that.
Okay, keep going. I know we're over time, but if people want to drop out, they can. But I'll stay on to listen to the rest.
I will too.
Actually, it's just 2 slides. I think we have the planned switchover and then the resimulation. Maybe we can skip the resimulation since till everyone comes to
Yeah,
speak.
I think it's a
But I think we
topic
can go
for a
through it.
whole. Yeah, that we'll have a whole meeting on resimulation because not everybody's familiar with resimulation.
Yeah. Then
Okay.
this is the last slide.
Yeah. So the planned switchover. So unlike the unplanned switchover, it's a controller-controlled switchover where I mean you want to basically bring down the pairing and you want to do maintenance on one of the DSCs. So the controller basically goes and triggers the planned switchover. Once a planned switchover is triggered, basically there is a coordination between these DSCs where for a shorter duration, basically, so here the DSC1 is basically is active for VIP1 and standby for VIP2, and DSC2 is the other way. So it is still forwarding traffic for VIP1 over here. As you see here, the addresses are not withdrawn. The virtual IP is not withdrawn here yet. So, but what it does is it basically it notifies the peer DSC to become active. What that means is not to be standby for VIP1 anymore. If it sees the traffic at any time, start switching the traffic. So it basically prepares the other DSC also to be active at the time. And then it starts the FSM shutdown process, wherein first it will basically go and start withdrawing the BGP routes. Once the BGP routes are withdrawn, so there is a convergence, time for those BGP routes to be withdrawn, and so after that, basically the traffic will start going towards the DSC2 for all the both the VIPs. But the DSC1 has not removed the virtual IPs yet from the data path. It is still the virtual IPs are there. So this is the period during which it's all the in-flight data traffic are flushed out between the DSCs. And once all the so we do it in using timers. So once all the data traffic are flushed out between the DSCs, then the DSC1 will finally completely brings down the FSM and closes the connection between the DSCs, and DSC2 will at that point move to standalone, and it doesn't do any syncing between the doesn't send any packet or doesn't look for any packet coming from the other side. So basically it becomes standalone and it goes. So it has to be a very coordinated mechanism where we need to flush out all the sync packets and whatever that are that are there between the in-flight packets that are there between the DSCs.
So, or in other words, if I may add, we want to keep that 0 drop on planned switchover. So I think we prep the underlay, make sure the active whatever was the primary is drained from the underlay perspective, and then bring up the standby so that way there is no drops.
Hi,
That is,
this is
yeah.
Jay from Microsoft. I have a quick question. when we start the HA switchover, the VIP1 becomes active also in DSC2. And what happens if there are two active VIP in both DSC1 and DSC2? And why can't we just switch switch to the standalone instead of being two VIPs being active?
I mean, in standalone mode, basically we don't honor any sync packets coming, or we don't send any sync packets. More than sending sync packets, anything that is coming from the other side is also not honored. So that means whatever in-flight packets that are going between the DSCs, they all will get dropped. So in order to do it in a graceful way, we put them in a kind of the data path in the active state, and we honor those packets, and then we in a coordinated way we gradually move to the standalone state.
If I may add,
think...
Balki.
Yeah.
If I may add, so I think the route, whatever is the VIP that the secondary advertises, is always an inferior, from the metrics perspective, it is an inferior. So from the, if your question was from the underlay, is there two paths leading to both? That doesn't happen because the primary withdraws whatever it has, this thing, and only after the primary withdraws will it switch over to the standby. It is not like both of them would be advertising and there is coordination.
So when, just a follow-up question here. So when two VIP1 is active on both DSC1 and DSC2, the traffic will still go onto the one of the DSCs?
Yes, it will always go to the primary for the VIP where it is primary, because of the route, that is because of the way the metric is set up.
I see.
By the
so
controller.
when the DSC2 changes the VIP1 from standby to active, does it change the VIP1 to be primary on DSC2, or is DSC1 still the primary of the VIP1?
DSC will still be the primary, but administratively, but it withdraws the route. There are a couple of other enhancements we're looking at, graceful shutdown and withdraw, but effectively it withdraws the route.
I think this one probably requires a lot of talk. I mean, even in Microsoft, we talk about this. So, what the best way to do this is, what's your last slide? I think is unplanned.
No, this
we
is the
went
last
through
slide.
the unplanned.
Yeah.
Okay.
This was the flow reason.
Okay. Well, so I think we've gone over time, but this is really good. I would like to see this as a pull request, so that people can read it, think about it. Also, like to, over time we can. I mean, this is, by the way, this is like most H8 devices today use some technique like this. I think we can do even better, but this is a great starting point, and at least for the most part, we know that this works pretty well. The switchovers, I think we still need to talk about, because we even talk about that internally. But I think generally, this is what I always call mode 1. This is like the classic one. And then we can talk about optimizations of this, and whether you need to send whole packets or you just send metadata, or you send more optimized messages. But I think from a starting point, I think this is excellent, and it's certainly logically true that it works, and so we should definitely do it as a pull request. Let people digest it for a little bit, because it's a lot to digest, and then like a couple weeks from now, we can kind of create topics around where people are unclear about this. And also, I do want, between now and then, to give Excite a chance to go over once more that what their pull request, which is not like the full, like, how do you do HA, but like what is the transport methodology that you could use to optimize HA. And I'd like to do that next week to give them a chance. They were going to do it this week, actually, but I think that this was important to bring, And then we could do like the Excite proposal, which I read, which sounds reasonable. I hope everybody's going to read their proposal for the transport protocol. And then we can, like in the following week, we can again come back to this and talk about potentially unclear parts, questions, and even optimizations that maybe Pensando thinks of or others might think of. So, but you know, excellent, of course, to bring something, you know, in such a complete form. I'm sure it's going to benefit the community tremendously.
Yes, thank you. Yeah, let's plan for Excite paper next week, Joe and team, and then we'll wait for the pull request or however this content is distributed. Balky, do you think you'll be able to attend next week?
The
meeting. The meeting.
Sorry, I didn't get it, Christina.
Do you think you'll be able to attend next week when we cover the Excite Labs proposal?
Sure.
Okay, I'll send it to you. I'll send you the link in email. Just so you have it.
Yeah, there's a pull request for it. It's really a transport protocol as opposed to the what you presented, but they can actually be used against each other to figure out is there optimizations that we can do. So I'd like
I'm gonna stop the recording now, guys. It was a long